Hello, and welcome to our webinar, FDM and PolyJet, Similarities and Distinctions. Before we get into our topic today, I'm going to give a little overview about who Stratasys is. For those of you who aren't familiar with the company, Stratasys Ltd. was formed in 2012 by the merger of Stratasys Inc. and Objet. The company manufactures 3D printers and materials that create prototypes and manufacture goods directly from 3D CAD files or other 3D data. The company's 3D printers are based on patented FDM and PolyJet technologies. We also operate Red-Eye On Demand, which is an online rapid prototyping and digital manufacturing service. Stratasys systems are used by manufacturers to create models and prototypes to aid in the new product design process. And they're becoming widely used for production of finished goods in low-volume manufacturing as well. So most of the content you'll see in today's webinar is based on a new white paper titled FDM and PolyJet 3D Printing, How to Choose Between the Top Two Technologies. At the end of the event, I'll let you know where you can go to download this white paper and other materials. So now I'd like to welcome our presenter, Mr. Fred Fisher. Fred is the Director of Materials and Applications Product Management at Stratasys. During his 15-year tenure with Stratasys, he's also served in roles of Marketing Manager, Product Manager, and Senior Applications Engineer. Fred has contributed to the development of new applications for additive manufacturing, and he has led global initiatives on application training and education. Fred holds a bachelor's degree in mechanical engineering from the University of Wisconsin-Stout. He's a frequent speaker at domestic and international events related to prototyping and digital manufacturing. And along with Fred, I'll be your host today, Kim Kaloran with Stratasys. So Fred, I will turn it over to you, and you now have the floor.
All right. Well, thank you, Kim. Hey, well, thanks, everyone. We're excited today to give a little bit of overview of where FDM and PolyJet are best fits in the additive manufacturing industry. So we'll go through the content and give both similarities and the uniquenesses of where FDM and PolyJet are best fits. Before we get started, one of the things we'd like to talk about is terminology. So we at Stratasys, and through this presentation, will use the term additive manufacturing to refer to a collection of technologies that I'll explain in a moment. But many of you on the call or in the webinar may recognize some of these other terms. 3D printing, rapid prototyping are commonly used terms to define what we today in the call will define as additive manufacturing. And what additive manufacturing is to us, it's a collection of technologies that are largely driven by three-dimensional digital data. That's the input. And what the technology does is in an additive process or in a layer-by-layer process produces a physical part, generally used as a concept model, a prototype, and even in some cases for manufacturing applications directly from that three-dimensional digital data, typically coming from CAD. So the process generally is three-dimensional digital data in, produce the part in the system or the technology itself, and then usually there's some post-processing that is required. Generally it's a support removal. It could be some other things dependent upon the technology. In general, if we look at the technologies that define the additive space and the process that many buyers go through when they're considering additive manufacturing, the first is that they will determine whether additive manufacturing is or is not beneficial based upon how they're producing their concept models, prototypes, their manufacturing parts, versus their traditional methods to do that. In general, the additive manufacturing space is made up of a number of different technologies, most of which fall into any one of these 5 categories listed in the second column there. Today what we'll be focusing on is where FDM and where inkjet, or specifically where PolyJet technology, are best fits in the additive manufacturing industry. So to help folks in the marketplace understand if FDM or if PolyJet is a best fit for their application needs. And so we'll talk about both the similarities as well as the uniquenesses of these two different technologies. So as mentioned, these technologies are both distinctly different, yet surprisingly different. It was one of the fundamental drivers behind the merger of both the two companies, or bringing these two technologies together, is the fact that they are very similar in many senses, both primarily from an operational standpoint, but they have very different outputs that satisfy different application needs. And thus, the two technologies collectively together solve a broader array of applications. Those applications can both be manufacturing or factory floor based, as well as models that can be used for concept modeling, for painting to look like the final production component, or models and parts that have the actual mechanical properties of the final product itself. So let's talk really briefly about each of these technologies and how they work. So we'll start with the FDM technology and talk about this. FDM, or fused deposition modeling technology, is an extrusion-based technology that uses a filament of thermoplastic material that's heated in a liquefier, and we very precisely control the location and the deposition of the material from the nozzle, somewhat like a two-dimensional pen plotter for those of you who remember how that works. So we very precisely control the deposition of the material on a layer-by-layer basis, and we repeat or build that part by building the very bottom layer and then extruding the shape of the layer on top of that, and repeating the process over and over and over again until you have your completed part. That's how FDM technology works. So again, thermoplastics in and a physical thermoplastic layered part out. PolyJet technology conversely uses inkjet technology to create the shape of each layers. So the material in is a photopolymer, a UV curable photopolymer that simulates thermoplastic materials or simulates elastomers with the PolyJet technology. And so how the part is built or printed, the model is printed, is the inkjet head passes over the part, and it very precisely controls the droplets or the deposition of these UV curable photopolymer droplets to create the shape of each layer. On the head itself, or the carriage, are ultraviolet lights that semi-instantaneously cure the material and then thus create the shape of the layer. And that process, again, is repeated over and over and over again until you have your completed model. So again, both technologies working in an additive fashion, but each technology using a unique material and a unique technology to create the parts. So what we'll explore now are three different categories to help understand where PolyJet and where FDM are best fits in the additive manufacturing marketplace. In general, we can organize things into three categories to show both the similarities and the uniquenesses. So operations, or how users engage and operate the system. The part characteristics, so what are unique about the actual output itself. And then the material options themselves, the diverse array of materials that are available to choose from to select the material that's best suited to the application. So let's first start, and we'll talk about operations, right, and how these are similar. The first category in operations is something that's oftentimes called speed. And there's two categories that we think are important to understand about speed. All too often, buyers get hung up and evaluate the actual build speed itself, right? So how quickly it takes to produce the part once the start button is hit on the system and the model is complete on the system. Now, this is an important data point to understand, but really what's generally more meaningful and more important to evaluate when looking at technologies is the total process time. The time it takes to go from the three-dimensional digital data, typically a CAD file, to the physical part in your hand or the physical model in your hand that can be used as a concept model, a functional prototype, etc. So it's really the time from the digital file till supports are removed and it's a usable part. That's what we call total process time. And that's what's generally most important and most relevant to look at, not just with PolyJet and FDM, but with all additive manufacturing technologies. So it's an important distinction we think is relevant for buyers as they look at technology. In general, PolyJet and FDM are somewhat similar in the sense of total process time when you're printing a single model, where PolyJet tends to have an advantage in the additive industry is where you start to build an entire tray of parts. There's a scalability factor, or where adding more parts to the tray generally tends to make the PolyJet technology and some other types of technologies more efficient. Looking at pre-processing, so this is the process of actually translating the digital file into the data that will run on the system. In general, both are relatively simple and easy to use. So there's a there's a software dedicated to both the FDM and the PolyJet systems that take the digital STL file in, and then the user makes their they select their parameters to produce the part and hit print and send the job to the system. And in both cases, pre-processing can be extraordinarily simple or somewhat similar and analogous to two-dimensional printing, where you set some very basic parameters, hit print in the system, or the printer continues to do the rest of the work or automatically starts doing the work. One of the differences is with FDM technology in the production-based systems or the Fortis systems. There's a bimodal support, software material, meaning the software can work in that very simplistic single-button fashion, or with the production systems from FDM, we give users the option to control all of the build parameters. And this is highly enabling when it comes to advanced applications where the end user can optimize how the part is built to enable the output to work much, much better for, in some cases, basic applications, but predominantly for advanced applications. Things such as thermoforming, maybe cores for composites, paper pulp molding, amongst many, many other advanced applications are enabled as a result of giving access to the operator to control the shape or the build parameters of their particular part. Again, both can work very, very simple and easy, but with FDM production systems, the access or exposure to those controls exists. Now let's talk about post-processing, or the processes that happen after the model or the part is completed building on the system. And in both cases, both with PolyJet and FDM technology, the post-processing is relatively simple. It's simply limited to removing the support structures from the model itself. This is somewhat unique in terms of FDM and PolyJet technology, where there's no curing or anything that needs to happen to the model to make it strong enough or stable enough to be used as a concept model or a functional prototype. PolyJet technology, or the removal of supports in PolyJet technology, is done in a water jet station or a water jet system. So the gel-like support structures that are used in PolyJet technology are washed away in what is somewhat similar to a sandblasting station, but rather than using sand, it uses pressurized water to break away the support structures from the model itself. The process is relatively quick, simple, and requires an operator for maybe about 15 to a maximum of 20 minutes, depending upon the size and complexity of the part itself. With FDM technology, there are two different types of support structures. There's a soluble and a breakaway. The soluble support structure, as the name implies, is a type of supports that are washed away in water, heat, agitation, and a cleating agent. So it washes away the support structures in an automated fashion, or it's a labor-free process. That takes generally anywhere from 2 to maybe 4 hours, depending on, again, the size and complexity of the model itself. There's another type of support material, or called breakaway support material, and as the name suggests, these are support structures where the plastic supports are actually manually broken or broke away from the model itself using some simple tools like a needle nose pliers as an example. And in general, like PolyJet parts, manually these supports can be removed somewhere between 10 and 20 minutes, again depending upon the simplicity or the complexity of the model itself. So this is post-processing. Again, very simple, relatively quick, and in some cases automated for both FDM as well as PolyJet. So, operations. The other thing is about where can the printer be put in the actual environment itself. Both FDM and PolyJet, one of the strengths when looking at all the additive technologies on the marketplace is the fact that the systems are clean, quiet, and safe. And as a result, can be inserted not only into maybe, let's say, an RP lab or a manufacturing floor, but they're also safe for office use and convenient for office use. And this is important when considering, locating the system closest to the operators or the people who will need to utilize the system, so it's convenient. It can be put in a spare office or maybe in a shared environment with both of the technologies. In both cases, potentially water or power would need to be plumbed or routed wherever the system, or more importantly, the support removal device is located. So many companies choose to put the printer very, very close to the engineer, designer, or manufacturing folks, and potentially to put the support removal devices in an area that's maybe more convenient from a power and water supply standpoint. So again, easy to put really close to the operators themselves. From an ease of use standpoint, overall, both technologies are relatively simple. When we talk about the materials that are required to be put into the system to run it, with both FDM and PolyJet, the material or the consumables come in fully enclosed cartridges or canisters, so there's no exposure to uncured resin or the filament of thermoplastic material, so they're safe and very easy to swap in and out of the system. Changing from one material to the next, so if you're changing, let's say, from black ABS to white ABS, or maybe Vero Blue to Vero White, or for that matter, from one material type to the next material type, is relatively quick and relatively easy for the operator to do as a result. So there's a semi-automation built into both systems to facilitate making sure that process happens simply and efficiently. In terms of starting a part, both systems are relatively simple. Maybe take a matter of minutes, maybe a maximum of 10 minutes from the time when the job is sent to the system, where the operator is at the system getting the system prepped and the part started. So really just a matter of minutes to get the part started. Both systems run unattended or lights out, in the sense that there's not an operator that's required to be present. So similar in the sense of two-dimensional printing, these three-dimensional printers or additive manufacturing systems work very, very similar in that sense. Both systems, as we mentioned before, have parts that are fully cured or ready for use directly or immediately while it's being produced. So in both cases, let's say you're building two parts in the envelope concurrently and part A is finished and part B is continuing to build, you can pause both systems, remove part A, resume the printer, and the system will continue to build part B seamlessly. So it enables operators to get their parts out of the system as they're ready. So, and then lastly is around operating expense. In this case, this is one of the areas of strength for FDM technology in comparison to all additive systems. FDM technology tends to be one of the lowest operating cost systems or total cost of operation technologies on the marketplace, both from the initial system acquisition, but more importantly, from the ongoing operating expense that's required. Generally, there's three things for FDM technology that drive the operating expense. The first and the most predominant of which are the materials, right? This is the filament of thermoplastic going into the system to produce the part, as well as the supports. And, a much, much smaller component of the operating expense exists around tips. These are the nozzles or the actual orifices in which the material comes out of, and the build sheets, which are the platforms in which you build a part on. So largely driven by materials, but to some extent by tips and build sheets. So again, FDM, very, very low operating expense compared to all the other technologies in the marketplace. PolyJet technology, the operating expense is largely driven also by materials or the UV curable photopolymer that goes into the system. The print heads themselves, or what's maybe analogous in FDM to tips, or these inkjet printing heads last somewhere in the neighborhood of 2,000 or more hours. So they have a very long life, but they are driven by the operating expense. They can be encompassed into some of the maintenance packages. And there's some miscellaneous odds and ends, small components of hardware that are a really small component of the overall operating expense, things like wiper blades, the roller knife, etc. So, in summary, looking at the various different operations, in general, both FDM and PolyJet are somewhat similar in the sense of the operations themselves, both from an ease of use, the process time required. Where FDM and PolyJet differ, PolyJet again tends to become increasingly advantageous or efficient as you build not just one model but many models in the envelope concurrently. And then conversely, one of the strengths of FDM in the overall additive marketplace is, of course, the ongoing operational costs as well. But again, both very easy to use, friendly to put in an office environment, and similar in terms of pre- and post-processing. So let's switch and talk now not about how the technologies are similar, but maybe where the technologies start to differ. And one of the areas is around the part characteristics themselves. So the first of which being surface finish. This is one of the things that PolyJet, surface finish being one of the things that PolyJet technology owns in the additive manufacturing space. Surface finish is generally largely driven by the layer thickness. So with PolyJet, it's either a 16 or a 32 micron layer thickness. So as a result, it has very smooth surface finish that's nearly paint ready. The surfaces can be sanded and polished to have almost a glass-like or an injection molded-like surface finish to it. That process is very, very simple and easy to do after the part has been, or the model has been printed. With FDM technologies, it's building in a slightly larger layer thickness, and as a result, the layer lines directly out of the system are certainly much more evident and visually apparent than maybe, let's say, PolyJet or some of the other additive technologies on the marketplace today. However, over the last couple of years, for those of you who haven't looked at FDM recently, there are a variety of techniques or post-processing technologies that Stratasys has optimized to work with FDM technology. Specifically, our finishing touch smoothing station, and really one of the more recent technologies called mass finishing, or the mass finishing, where we're really automating the sanding or the work that's done on the outside of the part to remove some of those visible layer lines and make the part itself ready to be used as a master pattern or to be ready for paint, as an example, to minimize the amount of filler or time that's required. So again, big strides made in post-processing techniques around FDM to improve the overall surface finish itself. And the next part characteristic we'll talk about is resolution and feature detail. Again, this is really driven in this case by both the dots per inch or the minimum bead width that either PolyJet or FDM technology can build. In general, this is again another area where PolyJet technology tends to shine or be positive. It is around being able to build things like text, small texture, pins, so very fine features, let's say maybe smaller than 40,000ths of an inch, generally tend to be best suited for PolyJet technology. So if that's something that an end user is needing to do on a very, very regular basis, PolyJet may be a better solution in that case. If it's just occasional and the output needs to be more mechanical and structural, then FDM tends to own that with things like ribs, bosses, gussets, maybe where actual screws or mechanical fasteners or clips and brackets are going to be put together. FDM technology can oftentimes be best suited for that when looking at all the technologies on the additive manufacturing market. The next is accuracy, and accuracy tends to be something that's oftentimes misunderstood, or resolution and accuracy are oftentimes intermixed amongst themselves. So what we previously talked about with resolution is really, and surface finish is largely driven by the layer thickness and isn't necessarily directly related to the accuracy of the part. So accuracy being how close the actual output is to the nominal dimensions of the digital file coming in, or the STL file. So how close to, let's say, 1 cubic inch or 25 cubic millimeters is this particular part. Both with FDM and PolyJet technology, when looking at all the technologies in the marketplace, are very similar and very good in the sense of the accuracy coming directly out of the system. Where FDM generally tends to shine is the stability of that part over time. So since FDM is using a thermoplastic material, that generally tends to be more stable in a broader range of heat, ultraviolet, humidity, and maybe even mechanical pressure exposure. FDM tends to be a more dimensional material over time with these exposures, where maybe some of the other technologies in the marketplace, either photopolymer-driven or even in some cases powder-driven, tend to be less stable as a result. So FDM really owns dimensional stability over time. But both technologies have very dimensionally accurate output directly out of the printer itself. So if it's a short life expectancy, either technology can work really, really well. If the part needs to survive for, let's say, not days but weeks or months, then FDM technology tends to be a better solution, or oftentimes chosen as a result of its stability over time. Next part characteristic we'll talk about is part size. For both FDM and PolyJet, the systems and printers that are available have a wide range of build envelopes that range from, in this case, about 400 cubic inches all the way up to 18 cubic feet, or 6,000 cubic centimeters, up to almost a half a cubic meter in volume. So there's a wide range that allows buyers to select an envelope that's really best fit, best suited to the size part that they're producing or the number of parts they want to produce on a regular basis. In both cases, both of FDM and PolyJet technology, parts can be built in multiple pieces and bonded together afterwards, so they can, if the part size happens to exceed the envelope itself. One thing to consider is the actual envelope dimensions themselves. While the cubic size is similar with both FDM and PolyJet, they somewhat vary in terms of their X, Y, and Z size, and then thus the size part that's being built or the orientation in which that part is being built can be an important factor to consider. In our spec sheets are quite helpful in listing out what those cubic dimensions are, and then thus the orientation that's relevant. With FDM, we also have what we call a small or an entry-level sized envelope, which is 125 cubic inches, or approximately 5 inches by 5 inches by 5 inches, rounded off, or approximately 2,000 cubic centimeters. So again, this is really best served for kind of a desktop, or maybe sharing the printer amongst just a couple engineers or someone who's building really small desktop-sized parts. And so in summary, looking at the part characteristics themselves, this tends to be where both FDM and PolyJet technology differ in the additive space. So surface finish and feature detail largely being two of the primary reasons why PolyJet technology is chosen in the marketplace, and the accuracy and stability of the FDM models and parts being one of the primary reasons why FDM is chosen in the market space. And in both cases, they solve a similar range in terms of size of parts that can be produced. The last category we'll talk about are the materials, or the materials that are available to run in the FDM and the PolyJet systems. In general, there are a wide variety of materials that are available for both PolyJet and FDM. In total, over 130 material options exist for photopolymers and thermoplastic materials. The photopolymers can be produced in two different types of material categories, what we'll call primary materials as well as digital materials. I'll explain what those mean in a moment, but in short, primary materials being printing the model in a single material, and the digital materials for photopolymers is where we're actually blending two different model materials together to produce the actual part itself, which enables changing the color or the grayscale of the model, or as well as the physical properties. And we'll explain this in a moment in more detail. All right, so let's take a look at the FDM and the PolyJet portfolio of plastics. If we plot those materials on a classic materials pyramid, that has standard engineering and high-performance materials, or as you work your way vertically up the pyramid, the materials become increasingly comprehensive in terms of their mechanical, chemical, and thermal properties. Both FDM and PolyJet have a portfolio of materials that fall into the standard category of plastics and photopolymers in this case. FDM actually has materials that also fall into the engineering and high-performance category of plastics as well. So in general, that drives FDM to be defined for performance-based applications. And as we've mentioned earlier, PolyJet is really driven by precision-based applications, or applications that maybe don't require as much mechanical, chemical, and thermal stability, but really benefit from the surface finish and feature detail that we've talked about earlier in the presentation. In both cases, there's a wide range of materials in terms of their characteristics, which are driven by the vertical columns that you see here, like rigid opaque, medical biocompatible, static dissipative, and rigid rubber-like. The wide range of plastics and photopolymers allow the engineer to choose the material that's best suited for their particular application. So let's take a look at the PolyJet photopolymers. In general, as we've referenced earlier in the presentation, PolyJet is all about simulating the look and the feel of the actual product itself. So it comes very close in terms of the aesthetic output from injection molding or maybe traditional manufacturing-based technologies. There are a variety of different material types that allow the end user to produce parts that simulate elastomer or rubber-like materials, or produce a rigid part, as well as change the transparency or the opaque nature of the output itself. Now, that's done in general by the primary materials, right, or by building a part from a single material. What makes PolyJet technology unique in the additive manufacturing marketplace is the ability to produce parts with digital materials, or blending parts or droplets from material A and droplets from material B. By doing this, it enables the end user or the technology to change the output in terms of the actual durometer of the rubber-like part, the grayscale of the component, and the mechanical properties of the part itself, as well as the color. Now, this also allows users like you see to build parts like you see in the lower right-hand corner of the screen, where actually mixing materials, or like the center of the hub is built in one material, it's a Vero White or a rigid material, and then the outer portion, or the actual tire itself, is built in a rubber-like material. So that is done, they're simultaneously jetted at the same time, and the part coming directly out of the system looks exactly like that. It's a compilation of those two materials. So it's an extraordinarily enabling capability that PolyJet technology owns, and really enables, again, the optimization of color, grayscale, and mechanical properties of the part, and specifically the durometer of the rubber-like part itself. Taking a look at FDM materials, again, in this case, it's all about the performance, right? Both from a standard engineering and a high-performance suite of plastic materials. So from ABS through Ultem, these materials generally tend to meet the most demanding application needs in terms of mechanical properties, chemical and thermal stability. So these parts are strong, they're durable over time, and in many cases they have unique certifications like flame, smoke, and toxicity certification for transportation-based applications, biocompatibility certifications, amongst others. So in general, where it's demanding performance requirements, FDM output generally tends to be one of the most chosen technologies in the additive manufacturing space. So in summary, if we look at both PolyJet and FDM technology side by side in terms of their materials, both have rigid materials, the PolyJet technology having a flexible material, FDM material having the most stability and durability over time. If you're looking for transparency, PolyJet technology is generally the best technology in high performance. FDM generally tends to be the best technology in the additive space. Both of the technologies have biocompatible materials that can be used for medical-based applications that come in proximity or in short-term contact with tissue or skin. So in summary, both FDM and PolyJet technology are similar in the sense that they're very friendly, office-friendly, easy-to-use systems and technologies that make the production of models both for concept modeling, for functional prototyping, as well as for manufacturing-based applications very simple and easy, generally saving time and saving money in comparison to traditional methods. PolyJet and FDM technology tend to be some of the most purchased technologies on the marketplace, owning over 50% of the additive manufacturing system sales in the marketplace today. And by combining these two technologies, it allows Stratasys and then our customers to solve a very wide range of application needs, whether they be flexible parts, rigid and durable parts, translucent or transparent parts. FDM or PolyJet technology generally tend to solve that application spectrum very, very well.
Great. Thank you, Fred. In a minute, we'll take any questions that you may have, and if you're thinking of a question and want to ask it, please be sure to submit it through the Q&A panel. I wanted to let you know that after the event today, you'll be able to download the white paper that was referenced earlier, along with the slides from today's presentation and the recording of this webinar at stratasys.com/webinar-fdm-polyjet. All right, so now let's move into questions. There have been a couple that have come in throughout. We'll try and get through most of these before our time runs out. The first question, Anna is asking, how much work is required once an STL file is sent to the machine? And do I need a separate computer for that STL effort?
Mm-hmm. Well, good. In general, good question, Anna. So in general, the process to start a model or a part once it's been sent to the system is relatively simple, right? Generally requires anywhere from just a few minutes to maybe 10 minutes maximum to get the system in a condition that's ready to start printing or producing the part. So it's quite simple. For the PolyJet systems, there is a dedicated workstation that sits next to the system, and this can be a relatively simple system, right? Today, one of these workstations can be purchased for, literally just a couple hundreds of dollars. So quite easy to have. For the FDM system, the computer, with the exception of the Mojo, the computer is actually built into the system itself.
Okay. Very good. And I also just am putting the final chart on the slide here, too, just if that helps raise any questions for others that may have a question to ask. We'll go on to another question. Hopefully that helped answer Anna. Bruce is wondering, is anyone using FDM for creating drill jigs?
Excellent. Great question, Bruce. So in general, one of the fastest growing applications for FDM technology is using the output not just for design applications but for manufacturing applications. And specifically, when we talk about manufacturing applications for what we call jigs and fixtures, or which would fall, or a drill guide would fall into that category. So many of our customers in the aerospace, the performance automotive, and in some cases even consumer products, amongst others, are using the output from an FDM system for a drill guide or a drill jig. In some cases where maybe the surface of which can't be plastic but needs to be metal of some sort, they actually press in a bushing, like a drill bushing or a drill bushing, to increase the wear resistance of that particular area itself. So again, in short, the answer is absolutely yes, and it's things such as drill guides are one of the fastest growing applications for FDM technology in our market.
Great. I think one more minute for one more question, and then our time is about up. This other question comes from Chuck. He's asking basically if parts are air or watertight from either FDM or PolyJet?
All right, good question. So the parts from a PolyJet system will come more watertight than FDM just due to the nature in which they're building parts. So it's always important to know the pressure of which. So if it's just ambient pressure, PolyJet parts are watertight and airtight for applications. Of course, it depends on the pressure itself, right? And depending upon the material and the geometry will determine at what pressure a PolyJet part can survive or can hold water or air. It's actually the same story with FDM as well. FDM parts generally tend to come out of the systems slightly more porous than a PolyJet part, but there are a variety of really easy and quick post-processes for FDM parts to make them sealed for either water or air applications and upwards of significant pressures as well. So some of our end users for FDM, and even in some cases for PolyJet, are using the output for things such as water pumps and impellers, actually testing those where the water tightness is important, as well as the ability to withstand and hold pressure.
And in some cases, too, the porousness, I guess, of the FDM comes in handy, like such applications like thermoforming, right?
Yeah, exactly. We referenced this earlier in the presentation. There are one of the unique capabilities of FDM technology is the fact that we can control the porosity, not just for the entire part, but actually in regions of the part itself. So applications like thermoforming, as you referenced, paper pulp, soluble cores are all enabled or improved as a result of the operator being able to have precise control over the density or the porosity of the part in a specific region, and that enables that application or improves our ability to solve that application.
Great. Well, that's all we have time for today. If we didn't get to your question on the call, we'll be sure to follow up with you after the session via email. Thanks again to Fred, and thank you all for your attention during the presentation. Now I'll turn it over to our operator who will close out the call. Thanks.